Oh, it's jolly.
You don't want to sit down, don't you?
No, we'll just get started.
Okay.
Okay, everyone. We're now come to the part of the program optimistically titled Panel Discussion, when a few brave colleagues have offered their services to come and sit at the front and discuss in free form various topical issues related to the workshop. So could I invite down Gert Aarts? Come on down. René Bellwied. Szabolcs Borsanyi. Francesco Renzo. So we've got about 45 minutes scheduled for this, and René, I think you've got some slides that you want to show.
Do you want the experimentalist to start?
Yeah, I'm actually going to start with you. So actually, before we start, I mean, perhaps everyone could introduce themselves, because not everybody has had the opportunity to speak yet. So can you say your name and what you know about?
So my name is Gert. I know a little bit about everything, and a little bit about everything, and not much about anything really. But I worked on Longevin for the last 7 years or so.
Yes, my name is Szabolcs Borsanyi. Right now I'm in Wuppertal. That means that I'm doing large-scale lattice simulations at mu equals 0, but also mu n equals 0. We have something, and I will mostly talk about things that seem to be doable.
Good evening, I'm Claudia Ratti, and lately I've been working on the lattice, but my background is also in phenomenology, so I try to connect to experiment, and I work on the QCD based diagram.
So this is Francesco. My way into the subject was actually algorithmic, as you saw previously. So my main interest at the moment is in timber regularization. I try to speak to other colleagues of mine. So one thing I would like to talk to you about is what people involved in gravitational waves are doing and why they depend on something which maybe we can provide, or at least try to provide.
Okay, keep that for. René.
Hi, I'm René Bellwied from the University of Houston. I'm actually an experimentalist. So I think Uli kicked off the panel because people recognized finally that he's not an experimentalist. So I'm actually an experimentalist. I'm on STAR and I'm on ALICE on the two heavy ion experiments. And I think what I recognized over the last 2 days is that you guys really want to solve the sign problem. So I got this, you really want to go to finite density. And I think the question to an experimentalist would be, if you would solve the sign problem, would we care or not? And that depends on how narrow-minded you are. And what I wanted to do just as an intro is I show you 6 variations of very colorful phase diagrams. Should probably take 1 minute, and each one makes a slightly different point. So my first point would be, this is what we call the LHC ellipse. So if you work at the LHC, you really don't care about the sign problem. As high as you can go with mu b is probably 1 MeV, maybe 1.5 MeV, depending on the centrality that you choose. If you work at RIC at the highest energies, again, what we get out of the data is the highest mu b value you can reach is probably 25 MeV. And again, I think that you can nicely do on the lattice, which just assuming that you have mu b equals to 0.
How do you read that off from that plot without scale?
I'm going to give you the numbers a little later. These are the little ones that I chose off of Wikipedia just to give you some certain ideas. This is the RIC regime where RIC got a second life, effectively doing beam energy scan. So step to lower and lower energies, and I blew this up a little bit here to show you. So the high energy was always 200 GeV. We did 39, 27, 17.5, 11.5, 7.7. We have a point at 5, one at 14 GeV. And you see you starting to reach out to the baryochemical potential. And on the last slide, I give you a table where you can read the numbers for all of those. The other point I want to make, because Gert reminded me of that, is if you work at low temperatures, from an experimental point of view, you actually have two regimes. You can look at the neutron stars, and I think that's always like an area for accelerated experimentalists that's really not very well defined. I mean, the only thing you can get here is probably radius over mass ratios or something like that. It's not so clear how you really do a direct link to lattice like we do it in the heavy ion experiments here. But the other thing that exists, and this is data from over 20 years ago, is a liquid gas phase transition that happens at about, people claim that the critical point here would be about at 16 MeV or so. So if you do low temperature lattice QCD or effective field theories, maybe this is something to work on. The point of this is that the data are 20 plus years old. Nobody has looked at them for many, many years. And effectively what you measure here is fission processes and intermediate mass fragment ratios. And I don't know, again, how they would relate to lattice QCD order parameters. So I'm not sure. But I just wanted to point out that these two regimes at low temperature also exist. Now, the future is such that the heavy ion people will go to lower energies. Two machines are proposed. The one is the FAIR accelerator at the GSI. And this is a trajectory, schematic again, which regime it might or might not map out. And the other one is Nika in Dubna, which would have even lower energies. And one caveat always is, because these are public relations plots, so all the trajectory reach nicely into the quark-gluon plasma, so they will not, right? At some point, your trajectory will simply not breach the difference between the plasma phase and the heavy ion and the hadron gas phase, and you have to remember that. And the last two I wanted to show you. Again, here is what you can expect from Rick and the future experiments, and then how close or how far away this would be on a mu-b scale to neutron star physics and so on. And another thing, this is a very, very old plot, but I just dug it out again because I think there's a lot of work going on this. This is the chemical freeze-out lines that you can get from statistical hadronization models, but now also, since recently, from first principle calculations from lattice QCD related to fluctuation measurements in the experiments. And this is an old version of the lattice QCD line, and that's also interesting because many people work on the curvature of this line. And one of the big questions for the experimentalists was always whether this curvature really stays like this, or whether this curvature at finite mu-b comes closer to the chemical freeze-out line or not, or whether you really increase the gap between the lattice pseudocritical temperature line and the chemical freeze-out line more and more and more. So that's something worth looking at. So the final slide I have, and then I have something more about data where we can come back to this. These give you the numbers. This is a compilation from 2006 with the old experiments. So this is RIC, this is the SPS at CERN, this is the AGS at RIC, and this is CIS at the GSI. There was a lot of refinement in the temperature scale of this, and some of this has changed, but the mu-b is always pretty solid. And you get this effectively by determining the mu-b from chemical yield measurements that you get for all the different particles. And you don't have to read the whole thing. There are some slight differences between different models, but here's what I can tell you. If you go to RIC, you cover between 25 and 600 MeV. If you go to CBM at FAIR, you cover between 350 and 800 MeV. At the NHC, you would not get nothing. Now, with respect to that scale, just let me make one point that I want to stress. There is no evidence for reaching the pseudocritical temperature in experiments that go above 500 MeV mu-b. So at some point, your trajectory will just not reach into that phase, and then there might be a critical point beyond 500 MeV, but you might not be able to see it in the experiment, and then it's an interesting exercise theoretically, but experimentally you will not be able to see it.
These temperatures and chemical temperatures, were they freeze out, or?
These are chemical freeze-out temperatures, but they have changed. There's a lot of work on this. I think the last word on this is that all the chemical freeze-out temperature lies slightly below the pseudocritical temperature you get from lattice QCD, which right now is 154 plus minus 5 or 9.
If you look at the numbers up there, the first one is 177 plus minus 7, which is clearly above any estimate you can get from lattice.
And that has been revised. These numbers revised if you include more and more particle states into your chemical fit. And it's unfortunate because this is a very highly cited paper. Braunzinger Stachel has 400 some citations, but they revised it themselves and they're now at 156 MeV. So don't look at the temperature so much. Nothing ever has changed in the mu-B scale, though, which should be important for this discussion.
So deep down, I mean, we've been staring at these phase diagrams for a long time, much longer than I've been around. What parts of them are we going to know very accurately, sort of GPS level, and what part is going to be some dragon breathing fire at the corner of the map? I mean, what are we ever really going to know about the QCD phase diagram? Anyone? Brave.
So perhaps I start from the easiest start, right? We already know much about it, well, at least one point. Where is the phase transition at mu equals 0? Although we also know that there is no phase transition, so it would be phase transition, at least some crossover, and we can very well describe this crossover, but it's still not what you are interested at least not in this panel. So what one can do is to try to ignore the sign problem, meaning that if you just want to address small chemical potentials, then it's mild, or you can just go brute force. You can invent something beautiful, like an idea with analytical continuation, but not solving, but circumventing the sign problem. And then the question is how far you can get. And there is a continuous effort by Bielefeld group, and we'll hear that tomorrow, but also from the Wuppertal group, also from the PISA group, to do this analytical continuation or Taylor expansion or reweighting. And all in all, what seems to be doable is ratio mu equals temperature. That's always setting the limit. It's not mu in MEV, but mu over temperature. And where we are right now is about value of 2, which might be pushed to 2.5. But we are still below the highest number that René has quoted, so there is still room for improvement. But
that's mu baryon we're talking about.
Baryon, yes, mu baryon. It's unlikely to be shifted to very high values. We have more chance to improve on this in the deconfined phase, but in the confined phase or right at the line, we are bound to fail if there is a critical endpoint.
Maybe I can also add that we know the curvature of the phase diagram, at least with the present level of accuracy. So we calculated that, and it's a very small number so far, if mu equals 0.
So the top left, there's some hope. What about the bottom right? Does anybody want to say anything? René's told us we know where the onset is. We have some evidence from experiments about the liquid gas transition.
Yeah, so the onset was interesting because we discussed yesterday, and I mentioned that somehow our holy grail is to get the silver blaze region right, which is where this onset happens. But then, as from an experimental viewpoint, it was, well, this is old physics and has very different physics. It's nuclear physics and fission and so on. So that's quite interesting because in Langevin, for instance, but also in all the other methods, somehow to get the onset at the right point seems to be the most important thing, just to prove that the algorithm is working well. So to answer your question, I would say we're not yet anywhere near to figuring out the phase diagram at low temperature, but one way to test the algorithm is actually to go to that regime and see whether it works. But then, of course, if it works, then there is all this complicated physics that is going on there, which has to be captured by QCD in principle, although even probably nuclear physicists will think about it in a completely different way and not in terms of the QCD Lagrangian. So that's an interesting. So we might be very enthusiastic that we can solve the silver blaze problem, but maybe nuclear physicists will think, well, this is completely different physics. So that's just something that came out of our discussion yesterday.
Maybe we could change tack a little bit now and talk more about the algorithms and the methods. Het.
Yes.
How long will it be before you entrust the life of a loved one to the complex logic of an algorithm?
I don't have any loved ones. No, I think my attitude is that it's what is exciting. So there's several things that are exciting. One of them is that obviously Langevin had a lot of attention, a lot of talks in the labs conference and here. And in particular, there are now 3 groups or so that do full QCD. So that's obviously extremely exciting. But on top of that, there are other algorithms as well, such as the symbol and then the states. And I think that's completely healthy and natural because that pushes the different approaches forward. So I don't particularly care which algorithm will eventually solve the sign problem, although I have preferences. But what is really important are different approaches that are pushing each other forward. And already in the past, I started working in 2008, so in the past 8 years, it's really been the friendly competition between the different approaches that has helped to move forward to some extent. So I'm happy with that.
Francesco, do you have anything you want to add?
Well, honestly, we are still quite far from providing, real numbers. I completely agree with what Gert was saying before. So, some sort of friendly competition, but some real attempt at really getting in touch and try to understand what are the relative merits, maybe even more than what we can fail in. That could be really important. Can I go back to your previous? Because that is a thing I was trying to deliver before, which looks like a joke, but okay. Till now, we have really thought of all this business having to do with people at RIC or LXC and so on, PSI of course. Then when it comes to neutron stars, it seems like, okay, but there is no lab for that, which is true. But in a sense, things are changing.
There's a poster outside constructing the neutron star.
Yeah, exactly. And I was, we were talking a little bit after that. And usually the point is, what in the end do you think you have to compare to? Well, at the moment we saw this spectacular improvement for gravitational waves. All the point is that they need a huge database of wavelengths in order to recognize what's going on. So people have thought quite long that, okay, there is no hope. In the end, one wavelength was recognized to a spectacular precision. Now the point is, people involved with binary neutron star, they depends on the equation of state. Okay, so the right hand side of the equation of Einstein equation has to do with the energy momentum tensor, and that is fixed once again by hydrodynamics once you know the equation of state. They are now at the level of simulating different initial conditions starting from different modeling of the equation of mole or of the equation of state, and their claim is that they want to validate different equation of states out of what they can match or not match. Of course we can say, just people were saying before they found the signal, okay, you're never going to succeed. Okay, but again, from another point of view, it's interesting to see that there is another community which is now deeply involved with that.
I completely agree. It always struck me when there was a lot of excitement about the phases at asymptotically high density and the superconducting phases. That's what attracted me. But you've got to know the equation of state from the onset upwards, otherwise you can't say anything. You don't even know if these phases are in our universe.
Can I make another joke?
Please do that.
The older I get, the more surprised I'm getting looking at how many applications hydrodynamics has.
Okay. Let me ask you another question about your great age in a minute. So, I mean, sure, go ahead.
Yes, so about this neutron star determination of the equation of state, I looked a little bit into that, and the progress is, like he said already, really interesting, because there are even processes out of which you can determine the equation of state by means of Bayesian methods, just based on the data that you have. So they are planning to, because not only the mass and the radius can be measured now, but also more differential observables like the moment of inertia of the neutron star, and that will really help in determining the density dependence of this quantity, and really from just constrained from the data.
Just another comment. I mean, going along with what you said, it's been. I'm a spectator in this, but it's really nice to see these different. I'm going to say competing methods for doing these, bringing these simulations into a new regime. There's a good feeling in the room. There's a definite feeling that some progress is being made. But do we need to look outside the room as well? Is there anything we can learn from other communities in solving these kind of problems?
Well, I would just make a comment because when you look at it from an experimental point of view, and one of the big things, if you look at the machines that are being built now, is really the question of whether there's a critical point between the hadron gas and the quark-gluon plasma, and a lot of that was based, and still is based, on effective field theories rather than the things that are probably discussed in this room, right? And the question really becomes how much credence one should give to that compared to an expansion in UB, wait for a solution to the problem. So, I mean, let me just I show you a plot and you can comment on it.
Okay.
Because that is, we call this the star map, but this was very highly discussed in our field. This is it. I don't know whether you guys have seen it.
This is a present compilation of every single model prediction of the critical point location. Basically.
Well, one of them must be wrong.
So I think most of those are what we experimentalists call effective field theories, right? So there's some Dyson-Schwinger stuff on it, and PNGL models, and so on. So is there? So let's say my question: is there a healthy competition, or is this considered lesser work? And you know, I mean,
I think it's considered. I heard a very great physicist once describe this kind of work as fertilizer.
I'm always very happy to see any model which reproduces lattice QCD results, because when I do a simulation, I just get a number, right, a function. But the lattice QCD doesn't give me an understanding. It doesn't give me a nice explanation that, look, Szabolcs, you get this peak because this and this mechanism is there. It's a huge work after the production of a plot until you really know what's going on. And
so it's not right. You're not happy until you can understand it.
Which understanding is not coming from my own work. So I'm really relying on.
I have to say, I don't know that I agree with that. If I do a lattice QCD calculation and I agree with the quark model, I don't feel like I learned anything because I know the quark model is not right. So, I mean, but the lattice calculation is probably right. And even if by chance I got the quark model answer, it doesn't validate the quark model. So.
Yeah.
Really, you want to say something?
Yeah, I mean, I wanted to ask a question to the lattice community. And what we have learned thinking about analyzing the experimental data is that there is actually two ways of trying to go about discovering the critical endpoint. One is to go directly for the critical behavior that you would expect near the critical endpoint. The other is to find positive evidence for a first order phase transition beyond the critical endpoint, and then by interpolation decide that there must be a critical endpoint because you have no phase transition on one side and you have a first order phase transition on the other side. So in lattice QCD, as I understand, there are the camps that are extrapolating by Taylor expansion or analytic continuation, and they are searching for evidence for the expansion to break down as a sign for criticality. Is there also an independent or complementary effort that goes straight to the heart of seeing that when you go to sufficiently low temperature and sufficiently large chemical potential, you see a first order phase transition?
Well, yeah, so that problem would suffer from the sign problem in QCD, so you can't do those simulations. But then I would add that in models where you can do simulations, such as two-color QCD or strong coupling models, for instance, and there are quite a number of attempts to just map out the whole phase diagram, not starting anew with zero, but just looking at the different phases and the phase boundaries. And so I would say the technology is there, it's known how to do it, and so if the sign problem in QCD gets solved, then you can immediately adapt adapt the technology to that case.
Really, I mean,
How much do we believe there really is a first order phase transition there? Is that?
Well, we'll pass that question to Philippe.
Yeah, I was suggesting the same.
Well, there used to be a watertight argument that a critical endpoint must exist, but I'm not sure how watertight it is.
yeah, one more thing that I would probably like to see is that when you go from vacuum to nuclear matter, that it is actually nuclear matter. That the quarks are clustered into, and what kind of nuclear matter would you see? Would you see neutron matter? Would you see isospin symmetric nuclear matter? How would symmetry, energy, nuclear binding energy, how would all of these things manifest themselves?
It's look, I mean, the lattice community is only just at the stage of systematically incorporating isospin breaking into any kind of simulation.
But we're doing,
No, I think it's a
the
tough
whole
question.
QCD, they're doing calculations with, tritium and helium and, so deuterons. It's not a finite density, but that's real nuclei, starting from lattice QCD. So I think we understand the nuclear forces.
Maybe two comments I would say. So you can do finite isospin chemical potential, and there will be a talk tomorrow, I think. And there you can do the simulations, and you can exactly see what condensate forms at which chemical potential and what the nature of the condensate is. So it's a fine condensate in that case. So that question can be answered. And I think for the case of barium chemical potential, you expect something to happen at the barium mass at low temperature. There is something guaranteed to happen.
Binding energy, right?
Yes, but nice. So there's something is guaranteed to happen, and that is for sure.
This is interesting. It's bearing on another question on my list. What are the problems which we should be going for in lattice QCD full bore, and what topics are better suited to non-lattice approaches?
If the mic is with me, I would like to emphasize that this phase diagram, which you see on the screen, is one of the toughest challenges, but we do not need to start with what we cannot solve, but we can also address more and less challenging versions of phase diagram. One that has recently been explored is the one against temperature and magnetic field, since we know that non-central collisions have some magnetic field. The cores nuclei are exposed to magnetic field, and it has been actually mapped, and there is no side problem there, although that is technically challenging, and you have to develop always something new in terms of algorithms, not just go ahead. Even more challenging is the isospin chemical potential, as you said, and there large lattice artifacts are to be expected. But what is really unsolved is what Philippe was addressing at lattice conference, the Columbia plot. There the masses span the axis, and there it would be nice if we could compare with lots of other expectations, which are presently very vogue, and I could not tell in what part I should look for a transition in terms of masses. For which quark mass cells do we have a first order transition? For which quark mass cells do we have a crossover? Because whatever we know is insufficient to plan a large-scale simulation program. So this is a kind of a series of phase diagrams from the easiest to the most difficult.
Luca wants to make a comment, and I'm going to make him use the microphone because
I'm allowed. Sorry.
couldn't.
Well, I think one of the things which we did not discuss yet, and which for the next future might be important and interesting to look at, is the non-equilibrium.
Anybody want to pick up on that? Who wants the mic? More generally, does anybody want to make a case for non-lattice approaches?
So I come back to your question about non-lattice approaches. So there's a whole other community out there of people that come from quantum information and quantum computing background, and they are working together with experimentalists to tune models that can then be done experimentally in the lab in optical lattices, for instance. And those are models that very much look like the models that we study. So models with relativistic fermions, even though it's a non-relativistic lab system, interacting with Bose fields and interacting with gauge fields. And they are also in the initial phases, I would say. But they can do a lot if that goes on, they can do a lot of problems that are really interesting, such as finite density, real-time dynamics, non-equivalent dynamics. So that's a whole completely different, well, it's not a completely different community because some people from the lattice community have moved into that area, but it's at least a different community scientifically who are nevertheless interested in very much the same questions, but in slightly easier models up to now.
Claudia, do you want to say something?
Before, I would like to add about non-lattice approaches. So this plot, I think, makes the case that when we want something quantitative, we should stick to the lattice and not resort to any kind of phenomenological approach. But the qualitative features sometimes can be described, or some, like the case of color superconductivity came out of effective theories, and I think it's an important case to make that sometimes effective approaches can point out aspects that wouldn't be so trivial to understand just in terms of lattice. And the other thing I would like to say is that when it comes to comparison to experiment, which is what we are trying to do, some of the observables related to the beam energy scan, there also I see an application for more phenomenological approaches to build the gap between lattice equilibrium thermodynamics and the heavy ion collision system, which is quite complicated.
Paolo, did you have some?
Yeah. Just want to point out. I can't do short.
I know, but I'm enjoying this.
So just point out that there is another community that should be represented here, but it's not at all. That's low energy nuclear physicists who did an enormous project recently, like the last 10 years, in just taking phenomenological nuclear forces and building up nuclei. They have their own version of Monte Carlo, they have their own sign problem, and they pretty much solved it. We can calculate from what they call first principles, nuclei with 40 particles. But quite an accomplishment. Those people, they probably know stuff that we don't, and vice versa.
Are they working in Euclidean formalism, or are they stuck from Hamiltonian?
They are showing the short-Schroeder equation, so it's a little different the way they formulate. It's closer to what people in condensed matter do.
Yeah.
But still, it's a similar physics. So by methodology and because of the subject matter, they are studying not the right corner, bottom corner, but the middle bottom part.
We've got to get through.
Another reason to interact with those people is that they know quite a bit about the nuclear force.
Yeah.
They know nothing about the three-body force. And the three-body force was demonstrated by those calculations to basically tell what's going to happen inside neutron stars. It's very unlikely quark matter exists in neutron stars anyway. One way to fit those three-body forces would be to do a little, quotation marks, lattice calculation with a little box where you can fit 2, 3, 4 particles. Microcanonically or not, it doesn't matter, and just feed this result to them. With one number, they could fit essentially everything they need to do. You combine this with the phenomenology of neutron stars and the equation of state, the equation of state up to several nuclear densities is essentially determined. But anyway, so that's a suggestion for the next conference.
Thanks, Paolo. That point's well taken. Are you listening, IAC? Okay, Philippe.
I wanted to go back to the remark about color superconductivity and emphasize the danger of taking effective field theories at face value. So I don't want to be accused of being a critical point buster, but let me stress that this color superconducting phase is not characterized by any gauge invariant order parameter. There's no such thing. So there does not need to be any transition, in fact. There could be a smooth crossover going from very high chemical potential down to nuclear matter with no transition whatsoever. And there is a recent paper by Kurkela, Romachke, and Guarinen, who computed the pressure of quark matter perturbatively at one loop, I think, at very high density, and it turns out that as you decrease the density, the equation of state blends in well with the known equation of state for nuclear matter. So that this, I would take this as support for the absence of anything like a phase transition happening. So the phase diagram may still be just an empty sheet with a little figure corresponding to the liquid gas transition of nuclear matter. That is a logical possibility.
Thanks. Does anybody want to? Yeah, René.
I have a question.
Okay.
If I look at the two corners of the phase diagram and I say everything I want to know about past, present, and future accelerator physics can be solved by going out to, let's say, 4 TC. And then I look at the region, the high density region. Does that also automatically separate the methodology that people would be using? So in other words, if I do now, I think what the big collaborations are doing is Taylor expansion, they're doing reweighting. So, but then when you look at complex large event, it seems to reach much further out in mu B. Could one say, okay, if you just want to do accelerator physics, then you don't need this, you only have to focus on this, but if you want to go to neutron stars, you need a different method, and you really need to explore that further. Can one separate it that way?
Paolo's just said he doesn't think we're going to see any of these exotic phases in neutron stars. It's going to be all new applications of low nuclear physics.
But presumably with Taylor expansion, we'll never go out to neutron star densities, right? So.
Yeah, so I have an answer to that in the sense which separates the practical from the principle. And so the practical attitude is, of course, is that you compute what you can compute with the tools that you have. But somehow there is also this feeling of first principle. You have the QCD Lagrangian, so you want to compute the entire phase diagram, and then you die before you finish doing it. But that's this like a first principle drive somehow. So whether it's how useful it is in the short term or the long term is not. So how much you learn in addition to what is known from nuclear physics at low temperature, for instance, may not be clear. But it's more like it's like this challenge. That's how I view it.
Yonivar, will you shout or shall I run?
Oh, I think I can speak loudly enough. So yeah, I think. I think it's kind of interpolating a little bit between Philippe's and Paolo's comments. I'm staying down in the low temperature nuclear physics region. So there, I think there's quite a lot of unknown stuff about the equation of state there. So people are modeling neutron stars with sort of different equations of state and getting quite different answers. So I think that's somewhere where we really want to get the first principles calculations done somehow. I mean, I think the low energy nuclear physicists don't really agree completely. There's the known experimental fact of nuclear matter saturation, but I think as far as I get it, talking to nuclear physicists or reading what some of them say, it's still not quite. They still don't agree on mechanisms there. Now, there's another thing that's I don't know what people think about this this suggestion that some things, some issues of the phase diagram could possibly be probed in proton-neutron stars. I think Schaffner-Bielik has been doing some studies. I don't know, do you think that's completely off the wall, or?
Uli wants to come in.
No, I don't think it's off the wall, but I think what one has to realize is the incredible amount of security that has been given to the phenomenological community by the lattice community, providing, after a long struggle of 25, 30 years, a reliable equation of state at finite temperature and zero baryon density. That's a remarkable achievement and absolutely essential for the future of the field. And in that sense, I think really understanding from first principles QCD, high density, low temperature matter, high baryon density, low temperature matter is an absolutely must. So So when I asked these critical questions before about what will you actually see there and so on, that should not distract from the fact that I think this is an absolutely important goal that you should pursue, and you should die pursuing it if that needs to be it.
We identify you as a critical friend. Okay, we've got 2 minutes left. What is confinement?
$1 million question.
Go on, Paul.
So,
Go for it.
when in the good old days, when we had no quarks in our lattice simulations, we understood confinement because it was just the static free energy, the static bulk energy had this unending slope with a string tension, and or the Polyakov loop was an exact order parameter. Now the quark mass gradually reduced, and also the lattice artifacts reduced to the thing that we see very little information from the Polyakov loop. Of course it is rising, of course it has some inflection point, but it's never zero even if you are below the transition. So what we're trying to focus in order to describe the confinement. Remember that the TC from the chiral was known several years before the deconfinement. And the only way we could describe deconfinement was through some model assumptions, like you have baryons in the system, and then you know that fluctuations of baryonic quantities have to obey some rules, like the force of the fluctuation and second order fluctuation has to be equal if you want to describe a system as a bunch of baryons, or it has to be a bit larger than one if you have baryonic bound states. And suddenly what we see from that is QCD, that around TC it drops from 1 to near 0. And that was a clear sign that this is a description of deconfinement which has not the characteristic of a chiral transition, because we never use any of the chiral observers.
Anybody else? René?
Well, just with respect to this, I think one of the big issues in experimental physics that we feel is absolutely unresolved is the chiral symmetry restoration transition. So from an experimental point of view, any lattice calculation, there's a lot going on with spectral functions and so on, but anything that would give us a real signature of chiral symmetry restoration that an experiment could measure, that would be very much appreciated. I think that when you talk about chiral observables, they're not observable for us. So these are not real observables, right? So you have to change the language.
Smoking guns. I'm thinking of transport now. I mean, is it like a insulator to conducting transition when we go from confined to deconfinement? Suddenly it starts conducting all this stuff. No one wants to run with that. Okay. I think it's time to stop, isn't it, Mr. Chairman? So can we all thank our brave panelists?